very much nothing broken. That one at the end there, yeah. And I went back here and get the other one. So yeah.
Not all. Every now and again, like very dramatic. I'm always worried about getting down there.
That's not bad.
Yeah.
I'm quickly booking something else. I'm not available.
I'll take my time.
I don't mind presenting, but generally I kind of feel my projects are like they're just sort of not being worthy, you know? You know what I mean? It's probably yeah. All right. I think I think I came back to about I think I'm going back to oh yeah, interesting. I was just looking through the miniature lifestyle and again the nature of life. It was like right. Yeah, that's right. It's good for
I assume we're okay to everyone hear me? Yeah, I think okay. I think we're good to go. And I'm assuming that those online, if there are who have joined us, are able to hear us too. So on behalf of SEC, I'd like to issue a warm welcome to everybody for what I think will be quite a fulfilling evening talk. So just to address some housekeeping first, there are no fire alarms scheduled this evening. Be pleased to know. So if we hear the alarm, we're going to follow the 2 exit points, and then the in-house staff will guide us to the relevant muster location. In terms of just going a bit beyond housekeeping, in terms of feedback, we're keen to hear feedback so we can continue to improve and reflect. So at the end of the talk, there'll be a QR code which will appear. So you'll be able to scan that and leave your feedback. So I encourage people to do that if possible. In terms of just advertising the forthcoming talks we've got, which is nice to do before we start, we've got two talks coming up which have got international speakers. So I think that's definitely worthy of highlighting, so we can foster a good attendance if possible. So the first one of those in January is entitled Seismic Design for Functional Recovery, Progress and Pathways to Codification. That's quite an interesting topic. So I think if we can work together to give a get that attendance as good as we can, I think that's going to be beneficial for everybody. And then we're looking towards February, something different again, innovative floor anchorage systems for low damage seismic resistant building structures. And we've got a speaker coming from University of Arizona. So I mean, when we definitely want to try and get a good attendance for that one as well. So two interesting topics which are coming up. And to further highlight something which we mustn't forget, if you go onto the website and you click the Young SecEd tab, you will see an item come up under podcasts. And there's 5 already online which people can enjoy, particularly episode 5, which is Professor Calvi reflecting back on his career, and I think there'll be nuggets in there which many will benefit from listening to. So don't forget that, and we'll probably look to enhance that visibility of that podcast area in due course. So coming back to our evening talk today, we're going back into the hazard front with this title, 2024 UK Offshore Seismic Hazard Maps and Future Developments. Now, just to say a little bit about the speaker, who you probably have met and seen before. So this is Dr. Ilaria Mosca, who is a seismic hazard researcher at the British Geological Survey or Society. She holds a PhD in seismology from the University of Utrecht and has been working for BGS since 2013 after a PDRA in seismic tomography in Germany. Her work is focused on seismic hazard analysis at regional and local scales, including catalogue analysis, simulation of strong ground motions, and assessment of realistic uncertainties for different components of the hazard analysis. Dr. Mosca has worked on numerous scientific and commercially funded seismic hazard projects in the UK and worldwide, leading them since 2020. She represents the BGS in the British Standards National Committee for Eurocode 8 for seismic regions and is an ex-econo member of the European Seismological Committee. So it's a privilege to have you here, Ilaria, and we look forward to your talk. Over to you.
Thank you very much for the nice presentation, for the nice introduction, and thank you to the SecEd committee for giving me this opportunity to present my work here. The presentation is divided in 2 parts, as the title suggests. So in the first part, I will show you the 2024 UK offshore seismic hazard model and maps, so the individual components, the results. I will show a comparison with the 2020 onshore national hazard maps, and then I will give general conclusions. In the second part, I selected the 2 recent developments for PSHA in relation to the UK, which will be included in the next generation national hazard maps. There are many more developments in PSHA, ongoing project that for sure will be included in the next generation national hazard maps. I selected these 2 because I was somehow related to them. I will also give a very quick display on how the national hazard maps are currently used for the revision of the UK National Annex for the second generation Eurocode 8. So let's start with the first part. So the offshore projects ran between 2023 and 2024 and was founded by the UKRI Industrial Decarbonisation Research and Innovation Centre, IDRIC. There are 3 reasons why it was the right time to do this project. First, in the context of United Kingdom's decarbonization and net zero policy, the North Sea and the Irish Sea are playing a strategic role to meet these targets through the licensing of an increasing number of CCSR, carbon capture storage areas, which are showed in by the blue polygons in the left-hand side plot. The figure shows also other offshore structures, such as wind farm. The blue polygon describes the UK offshore exclusive economic zones, basically the UK commercial waters. And the yellow polygon describes the study area used to develop the earthquake catalogue. In the context of licensing process, it's important also to include seismic hazard analysis to ensure that the structure, the offshore structure, are not damaged in the event of ground shaking produced by future potential earthquakes. The second reason is that the map, so this region is classified as intraplate region with low level seismicity. However, as the map shows, there are earthquakes that occurred in historical time. They are described by the by the red circles. The circles are scaled depending on the magnitude. And in particular, I'd like to point out on this epicenter. This is the largest instrumentally recorded earthquakes in the region. It occurred in 1931 in the southern North Sea, and it was an earthquake of magnitude 5.9. So although such a large earthquake has a very low probability of occurrence compared to the probability of occurrence of other natural hazards, these moderate earthquakes can still carry a significant cost for the British society. And for this reason, it's important to have a robust estimate of hazard for offshore structure, including CCS sites. The last reason is that the previous hazard map offshore were published in 2002, and the slide shows the publication. And since then, there has been significant advances in PSHA, in probabilistic seismic hazard assessment. For all these three reasons, it was the right time to update the offshore maps. So we start with the first component, the earthquake catalog. The figure here shows exactly the same distribution of earthquakes showed in previous slide, but in this case, the earthquakes are color-coded, so the circles are color-coded based on the sources where the data come from. In this project, so the catalog produced by this project is very comprehensive and very complete offshore for the offshore regions, which was the focus of the project. In particular, we carefully merge data from different local monitoring agencies, giving priority to the local agency for a specific region. So this means, for example, that along the coastal region of Norway, we use data from North SAR or University of Bergen. In the Republic of Ireland, we use data from DIAS. In the UK, we use the data from the BGS database and so on. So this project, the 2024 project, took advantage, so benefit from an important improvement of the historical part of the earthquake catalog from the BGS database. This occurred between 2020 and 2021, so during the COVID lockdown. BGS staff helped to create missing digital face data for events in the BGS database that occurred between the 70s and the 90s that were previously missed in the database because they were recorded on paper. This amount of new data was used to relocate the events that occurred in that period and to re-estimate the local magnitude ML. Furthermore, the local magnitude was also adjusted using the correct factor for the Hood-Anderson seismometers, which was previously wrongly used. And this re-estimation of the local magnitude resulted in a slight reduction of ML between 0.1 and 0.2. The big benefit of this project was also that all earthquakes of magnitude about 2.5 and above in the instrumental part of the catalog are also associated with consistent uncertainty in the local magnitude. So if anyone use earthquake from the BGS database, please use the latest version, which have a re-estimation of ML, and they also have uncertainty associated with it. The big difference between the 2020 onshore project and the 2024 offshore project are a re-estimation of the completeness thresholds for the offshore regions. Generally speaking, the completeness analysis is a critical part of the catalog analysis. This tells us how complete is a catalog, and usually the completeness improves with time, so it's better close to the present time, and is better for large magnitude. So the results of a completeness analysis is a pair of numbers. The first is the completeness magnitude, MC, and the second one is here, which corresponds to the beginning of the temporal window for which the catalog is complete. So the slide here shows two tables. The one for the completeness results from the 2020 model, and the second one for the 2024 offshore model. For the UK, the completeness thresholds MC are pretty similar, are almost identical. In 2024, we added one magnitude thresholds more for 3.5, which correspond to the newspaper tax uplift across the UK. The big difference, as I said, is for the offshore regions. So in the 2020 project, onshore project, we use the results of the completeness analysis from the European Seismic Hazard Project share published 10 years ago. Last year, instead, in the 2024 model, we revised these results based on simulation of predicted intensity and the completeness results from Johnson et al. 1994, which provided the completeness thresholds for various stable continental regions. Using the global magnitude detection in the last century. So in particular, to get a sense of completeness thresholds for the offshore regions, so we simulated the expected intensity for an earthquake of magnitude around 4.9. This was an event that occurred in 23 March 2022, on 23rd March of 2022, in the Viking Graben, so northern North Sea. And it was the largest earthquake in the last 33 years in that region. For the modeling, we used two different intensity prediction equations, Allen et al., which was derived using thousands, tens thousands microseismic data all over the world, and Mosca 2013, which was derived using hundreds microseismic data around the UK. So the results are showed in the top plots, and where the red squares indicate populated areas where we receive a felt report from that earthquake, from the shaking of that earthquake. And the results tell us that the predicted intensity from Allen et al. Is slightly smaller than Mosca for an earthquake of about 4.9. In the second series of tests, we simulated the expected magnitude for an earthquake that would be felt at least by one populated place, described by the red square, using the same two intensity, with intensity of 3 across the North Sea, and we use the same intensity prediction equations. The results are given again by the two plots at the bottom of the slide, where the blue circles describe the earthquake catalog for historical time, so before the 70s. And in this case, the results tell us that using Allen et al., the equation of Allen et al., the expected magnitude around in the central North Sea is around 6.5, whereas using Mosca, the expected magnitude is a bit lower, 5.5, and it would be felt by the population along the coast. So both results do not really fit with the threshold, with the completeness thresholds used in 2020. And furthermore, the results from Mosca et al. Fit quite well with the thresholds provided by Johnson et al. And for this reason, we decided to use this one. So the slide here shows an overview of the seismic source logic tree for the seismic source characterization model. Red numbers indicate the weight associated with each branch. So there are different levels of branching. The first one is the delineation of the source model, the geometry. The second one is the maximum magnitude, so the maximum possible earthquake that can be produced in the region. And this branching level is exactly identical to the 2020 project. Then we have the recurrent statistics, which consist of 25 values for each zone of the source models. Then we have the percentile depth distribution, which depends on the region, and the faulting time for the future potential seismicity, which is not showed here due to the large number of branches. So one of the big criticisms of the 2020 National Hazard Model was the fact that we use a single source model, a single source zone model. So in this project, in the offshore project, we improved this. We use 4 different source models, which are showed in the next slide. The geometry are showed in the next slide. Generally speaking, the source zone model consists of a series of zones where the seismicity is uniform in character within each zone. The source zone model could be also fault sources, so active faults. In the UK, usually active fault sources are not included in the source model because there is a lack of information about the geometry of the faults at depth, and we cannot really correlate tectonic structure with specific earthquakes. So the plots here shows the geometry of the 4 seismic source zone model. Red circles indicate the earthquakes within the completeness. So the first model is from the 2020 onshore hazard model for the UK surrounding region. For the other regions, we use the European seismic hazard model published a few years ago. The second model is a new model, a new source zone model derived for this specific project, which is based on the structure and geological understanding of the region. The other 2 models, so number 3 and number 4, are the source model published in 2002 for the previous hazard maps. The next branching level is the recurrent statistics, which is described by the Gutenberg rate exponential law to quantify the spatio-temporal rate of earthquake occurrence for a seismic source. So this allowed us to predict the frequency magnitude distribution, which tells us the expected number of earthquakes of a specific magnitude for a specific temporal window and in a specific source. Seismic source. The equation is given at the top of the slide, and it's a log scale equation described by 2 parameters. A, called activity rate, is the total number of earthquakes in the sample. B, called B value, describe the proportion of large to small earthquakes, and usually it's around 1. The equation at the bottom shows a variation of the Gutenberg rate frequency magnitude law, where the range of magnitude is limited by an upper-lower bound. Generally speaking, in low seismicity regions, such as the UK, it's not straightforward to have a reliable estimate of the activity rate and B value, because there are often not enough events within the completeness to constrain these 2 parameters well. And therefore, particularly for the B value, the uncertainty associated with it can be very high, very large. Here it's an example of the calculation of the recurrent statistics for the red polygon in the small map. In this case, I use only the instrumental part of the catalog within the completeness thresholds. We use the penalized maximum likely procedure to derive the recurrent statistics. This procedure has several advantages. First, it accounts for several completeness time windows. It considers the uncertainties in the recurrence parameters A and B, their correlation, and it also allowed to use a prior B value in case the zone contains very few events for reliable estimates of the B value. The results of this procedure is given by a matrix of 5 values for the activity rate times 5 values for the B value. And in total, this means having 25 frequency magnitude distribution described by 25 triplets of activity rate, B value, and their weight. And these are described by the gray and black lines in the plot. In particular, the black lines is the frequency magnitude distribution with the highest weight. And they are compared with the observed frequency magnitude distribution described by the red circles together with the error bars, where the length of the error bars is inversely proportional to the number of events for each magnitude bin. So this particular, the black line, whose parameters are given at the bottom of the plot, tell us that in that region we expect between 2 and 3 earthquakes of magnitude 3 and above every year, and about 0.0038 earthquakes of magnitude 6 and above every year in that regions, which correspond to 1 event of magnitude 6 and above every 260 years. And this recurrence interval is associated with uncertainty, which is given by the blue arrow here. So to give you a sense of how the recurrence statistics change from the 2020 project and the 2024 project, here I compare the zones whose geometry is identical in the 2 projects. There are 20 zones, and the 2 lines compare the recurrence statistics for the 2024 zone given by the black line and the 2020 zones given by the red lines. Overall, for the zone onshore, the agreement is very good, whereas for the zones offshore, there is significant differences. For example, in that case, this and here, you can see that the 2 lines are parallel, meaning that the B value is the same, but the activity rate for the 2024 zone is significantly higher than for the 2022 model. And this is a consequence of the change in the completeness thresholds for the offshore region. So now we go to the ground motion component of the seismic hazard model. So this is show an overview of the ground motion logic tree. Generally speaking, we use what is called the multi-GMP approach. So first, we select a large set of candidate GMP, ground motion prediction equations. We computed the ground motion predictions using these candidate GMPs, and we compare them with a set of ground motion observations for the regions. And this allowed us to select a small set of GMPs, which are indicated in the first branching level of the logic tree. We selected 5 GMPs, 3 are empirical models, ground motion models, 2 are stochastic model. Each is associated with a weight, and the weight results from the comparison between ground motion prediction observation, but also from discussion in the project team. And this is because the set of ground motion observations is very limited, consists only of weak motion, doesn't really include the recordings for large earthquakes. And therefore, it's not enough to be used completely to derive the weights in the logic tree. The logic tree, so the selection of the GMPs is an update of the GMPs that we use in the 2020 project. The second branching level is given by the host to target or VS-cap adjustment procedure. This adjusts the selected GMPs for site condition from the host region, so where the GMP were derived, to the target region. And the site conditions are represented by the shear wave velocity profiles, which describe the effect of elastic amplification due to the shear wave velocity structure, and the kappa zero values, which describe the near surface attenuation at the site. This branching level is exactly identical to what we use in the 2020 onshore project, because the VS30, so the shear wave velocity for the top 30 meter, has the same value, it's 800 meters per second. The kappa zero values are also the same. In this project, in the 2024 project, we added an extra branching level represented by the sigma model. Nowadays, it's state of the art to separate the logic tree for the median ground motion and the sigma model and the aleatory variability represented by the sigma model. And this is due to two reasons. First, to avoid the double counting, the aleatory variability when the sigma model from the individual GMPs is used together with the host to target adjustment. And second, it's because for the stochastic model, usually the sigma model is not well constrained. I don't go into details of this part. There is an extra slide eventually if there is time. So I want only to add that in this project, in the 2024 project, we use a larger data set of recordings for PGA, spectral acceleration 0.2 seconds and 1 second, which is described here as a function of distance and magnitude. And you can see the comparison, how that is the fact that it's larger than the one that we use in 2020. Still, it's a limited data set. It's consists only of weak motion recordings, but it's an improve for the future. Finally, I'll show you the results. So these are the hazard maps for the exclusive economic zone described the black polygon. These are for a return period of 475 years for big gun acceleration, spectral acceleration 0.2 seconds and 1 second, which are representative of short and long period. And generally speaking, the maps shows that the level of hazard is low in this region, increases slightly in the northern North Sea, in the southern North Sea, around Saltpeat, and offshore North Wales. These are the maps for 2,475 years return period. The pattern is very similar with a higher amplitude. We also did some site-specific seismic hazard results for three selected CCS sites described as the stars in the map. We selected these sites because they were licensed in the first round by the North Sea Authority, Transition Authority in 2022. They have different level of hazard. And furthermore, the red site, which is the endurance site, is very close to the epicenter location of the 1931, as already said. And the high net site, green star, is close to the high seismicity region of North Wales. So basically, in the last 5 years, BGS and the seismology team developed two sets of maps. One is for the onshore regions, it's the national hazard maps, and the second one is for the offshore region, the UK commercial waters. So we overlap. Let's overlap these two maps together. So this show the peak gun acceleration for two different return periods. And you can see that the agreement between these two maps done by two separate projects is quite good along the western coast, whereas there are some differences along the eastern coast. You see that onshore the color is lighter than offshore. And this is the same also for spectral acceleration 0.2 seconds. So generally speaking, there are no wrong map or right map. It's not that one set of maps is better than the other. It's simply that the 2024 maps are a natural update of the 2020 onshore national hazard maps, where we use the update data set and the latest methodology available for PSHA. So I give a quick conclusion about the first part. I want only to highlight one point, is that this offshore hazard maps will help to identify regions of high and low seismic hazard. Offshore will help provide a robust baseline model to discriminate between tectonic and geoseismicity due to the operations in case an earthquake occurs, and provide also first order approximation level of the seismic hazard for offshore engineering structure. However, obviously, they are not a substitute for site-specific hazard analysis, exactly because they provide only a first-order approximation level of the hazard. So all the decisions taken to develop the hazard model, source model, ground motion model, are taken uniformly across a large area and are not driven by a specific point, as it happens for the site-specific hazard analysis. Here there are some useful links and sources and resources. I want only to highlight 2 points. First, it's the first time that a BGS dataset for hazard is associated with the DOI, which is indicated there. So if you use this dataset, a dataset related to the offshore hazard maps, please use also the correct citation with the DOI. And second, similar to the onshore hazard maps, also the offshore hazard maps will be included in the GeoIndex, BGS GeoIndex, which is an interactive tool. And the GeoIndex is going through a revision. So there will be a new version of the GeoIndex, which will merge the old GeoIndex onshore and offshore. A beta version, so a testing version, is already available. Unfortunately, the hazard maps are not included in this beta version, but they both will be included. So now we go to the second part. So we start, I hope that there is time. We start with a smoothing approach. So in particular, so traditionally for seismic hazard analysis at regional, national, and also local scale, the source model is represented by the zoning, what is called the zoning model. So it consists of zones, areas where the seismicity is uniform within the zone. However, the main drawback of this approach is that there is a certain degree of subjectivity in the delineation of the zone boundaries, and this is particularly true for low seismicity regions such as the UK, because there is no really correlation between we cannot really correlate tectonic structure with specific earthquakes, because earthquakes have never produced surface rupture on the surface. To overcome this limitation, there is an alternative approach, the smoothing or zoneless approach, where which depends on the past seismicity. So the probability that an earthquake occurs within a zone depends on the smoothed epicenter location of past seismicity. It's higher, close to epicenter location of past seismicity, and lower, smaller, far in areas where past seismicity didn't occur. And this is true. This is done through a probability density function called the smoothing kernel function. On the other hand, the drawback of this methodology is that it relies completely on the past seismicity. So in regions like the UK, the earthquake catalog is not a good indicator of long-term seismicity because it's very short in duration and therefore doesn't really describe the entire seismic cycle. However, it's an alternative to capture better the epistemic uncertainty in this component of seismic hazard. There are several smoothing approaches published in literature. I selected the one published in 2019 by Asaturians and Atkinson. This is called the hybrid smoothing approach, and it's developed for Monte Carlo-based PSHA. So I selected exactly this one because in BGS we conduct seismic hazard analysis using a Monte Carlo-based PSHA. So, and therefore it was straightforward to implement this methodology in the BGS in-house software. I don't go into details of the methodology, but there is a report with an internal BGS report which compare two different smoothing approaches and which compare different parameters to set smoothing kernels. And before going to the next slide, I also, so this is a kind of hybrid smoothing approach because the concept of the zone is remain. So basically, the smoothing kernel function depends only on the distance, but not on the magnitude. So they don't control the rate of earthquake occurrence for the future seismicity, which depends still on the Gutenberg-Richter distribution, frequency magnitude distribution defined for each zone. So the concept of zone is still remain. And for this reason, it's called hybrid smoothing approach. So the obvious question now is how does the hazard change if we use a smoothing approach rather than a zoning approach? So I did this test for the 2024 hazard model using the 3 CCS sites. The results here are for PGA. And for the Acorn and the endurance, for the Acorn and the HiNet site, you can see that the hazard using the hazard curves, using a smoothless approach is smaller than using a zoning approach. So the dashed line describe the smoothing, the results from the smoothing approach. The dotted line describe the results from the uniform seismicity approach or zoning approach. The solid lines describe the results using a combination of them with equal weights, and that's why it's exact in the middle. For the endurance site, instead, red lines, you have exactly the opposite. And this is because the hazard using a smoothing approach is influenced, is affected by the epicenter location of the 1931 earthquake. You can see this better in the hazard maps. Top panel shows the hazard maps using a smoothing approach for two different return periods for peak and acceleration. The bottom maps, the maps at the bottom of the slide shows the map that I show you in the first part. Using a smoothing approach, generally speaking, the hazard reduces in the regions of low seismicity and increases in the regions of high seismicity. So, for example, in the northern North Sea and the southern North Sea. Furthermore, using a smoothing approach, you can see the typical bull eyes pattern, which is due to the smoothed epicenter location of the past seismicity. I didn't say that the left-hand side plot or the right-hand side plot shows instead the distribution of main shocks to be able to relate the pattern of the hazard with the location of the seismicity, of the past seismicity. Basically, this is an alternative approach which can be used in the next generation hazard maps to capture better the epistemic uncertainties in the source model. Care obviously must be taken to define the weight within the logic tree for these two approaches. The second part, so the second development is about the ground motion model. Modeling. Generally speaking, there are two approaches to capture the variability in the median ground motion. The first one is the multi-GMP logic tree approach. We already discussed this. This was used in the 2024 offshore approach, offshore model, and also in the onshore model in 2020. The second one is the backbone approach, where the median prediction of the selected backbone model, which can be one or more empirical GMP, is adjusted, so scaled up and down to account for source path and site difference from the host to target region. In some way, this approach is more transparent to track the epistemic uncertainty in the ground motion and to see how they propagate into the hazard. However, it requires consistent, a large number of data to be properly calibrated, not only ground motion recordings, but also all possible source parameters for the earthquakes that occurred in the target region. So last year there was a ground motion backbone model published by Douglas et al. This was derived using the hybrid stochastic empirical method based on existing ground motion model for California, that was the Chio and Yang 2014, one of the NGA West 2, and the stochastic model for the UK developed for this specific project. I don't go into details of the model. There was a second evening seminar last year. Here I want only to compare with the multi-GMP approach. So first of all, I should say that the backbone model has several versions. One is the full version with hundreds of branches, and then there are two other versions for engineering application. Here I use the 3-branch backbone model. And the ground motion prediction from this model is described by the 3 plots, by the yellow lines, as a function of distance for 3 different magnitudes, and they are compared, these predictions are compared with the ground motion prediction from selected GMPs. And what we can say immediately is that the yellow lines envelop the other models, indicating that probably capture well the epistemic uncertainties in the median prediction. Again, now the obvious question is how does the hazard change if you use this model rather than the multi-GMP approach in the UK or in the offshore region? So we did this test again for the offshore model. And the results here shows the hazard curves for the 3 CCS sites for big acceleration, spectral acceleration 0 to 1 second and 1 second. Dashed line describe the results using Douglas, the backbone model of Douglas et al. Solid line describe the results from the 2024 ground motion model. And in all cases, you can see that there is an increase in the hazard using the backbone model. So the increase is up to 40% for a return period of 2,475, and for the endurance site, 4 PGA. So the conclusion is that it seems that using a backbone model rather than a multi-GMP approach, the epistemic uncertainty may be captured better. There is also another backbone model underway by Professor Stafford and BGS. This model is not completed yet, so I cannot really show you the model. I cannot show you how the hazard change. I want only to spend a few words about the data set. So we put together more than 1,000 ground motion recordings from 41 earthquakes. And after a visual inspection of each of them, we selected only 500 records were accepted from 37 earthquakes. The earthquakes are described by the yellow stars in the right-hand side plot, which shows also the distribution of stations for the UK monitoring network. Central panel describe the records, all the records described by empty circles, and the accepted records described by colorful circles. The colors depends on the earthquakes. And these are a function of distance, so from 0 to 500 kilometers, and local magnitude from 3.5 to 5.22. Rejected records are those that are only for the vertical components, so from all earthquakes that occurred between 80s and 90s, between the UK monitoring network was upgraded with broadband seismometers, or are rejected records are those with abnormally high spikes in the time series, or with missing data in the time series, or those with a very low signal-to-noise ratio. The last plot here shows the density of the array coverage for the accepted records. And you can see that the coverage is relatively good in the East and West Midlands, is less good in South England, and is very poor in Scotland. The advantage of this dataset, which was also used for the 2024 offshore project, is that all the records are uniformly processed. And the next slide shows an example of the processing procedure. The example is for the Grisby earthquake that occurred in 2018. It was an event of magnitude 3.8 ml. And I selected a nearby station at a distance of 28 kilometers, as you can see from the map. So in the processing is probably quite standard. So the waveform are corrected for the instrument response, and they are provided with the physical units. There is a baseline correction to have a zero mean of the signal. Then there is the PNS peaking. We analyze the signal to noise ratio. And then we defined the usable frequency range given by the green lines here. And this usable frequency range is used to apply a bandpass filter to get the final processed outputs, which are given by acceleration spectra, displacement spectra as a function of period, and the areas intensity together, the areas intensity, together with a significant duration between 20 and 80% of the areas intensity. If I have time, I have two slides about how the 2020 onshore hazard maps are used to revise the national annex of the second generation Eurocode. So generally speaking, the implementation of the Eurocode is provided by the national annex by the individual countries, which calibrate the seismic design requirements of the engineering structure to the seismicity level of the UK. One of the changes in the Eurocode is that the seismic design action is described not by PG8 as in the previous version, but the spectral acceleration for a short period, so at the plateau, and for the UK, and by spectral acceleration at 1 second. The reference period is 475 years. And for the spectral acceleration short period and 1 second, they are given by the hazard map, the national hazard maps. So for the UK, these are the hazard map published in 2020. So the next step is to go from the seismic hazard spectral acceleration to the seismic design. So this slide shows the hazard maps published in 2020 for spectral acceleration at 0.2 seconds for 475 years. This is exactly the same map, but the spectral acceleration are grouped into seismicity classes as indicated by Eurocode 8. And this map tells us that all the UK, most of the UK is classified as a very low seismicity region, except a small, the tiny region in Northern Wales, which is classified as low seismicity region. The next step is to go from spectral acceleration 0.2 seconds to the seismic design index S delta. The formula is given in the slide. And this function depends on several parameters, including the type of buildings and the soil conditions. Some of these parameters are calibrated, should be calibrated for the UK, should be calibrated for the seismicity level of the UK, and this work is still underway. So what I'm showing here are intermediate results, are not final results. Using the values provided in the Eurocode 8. So the two maps in the left-hand side of the slide shows the distribution of S delta grouped using the classes provided by Eurocode 8. And you see that most of the UK, again, falls in the very low seismic design class. This is described by the greenish color, except for the South Wales, the Mid Wales, and the North Wales, which fall in the class of low seismic design class. These two maps are for a building type CC3A, which are buildings with social purpose, such as schools, and are for two different site classes. One is B, so generic rock condition. The second one is class D, stiff soil conditions. Now we go to another type of buildings, the CC3B, which correspond to buildings of buildings of vital importance during earthquake emergencies. So the example of these are, for example, hospitals and fire stations. And you can see for class B, the distribution is similar to the previous two. For class D, instead the bluish area is larger, include all Wales and central England, Western Scotland, and there is also a tiny regions which is pinkish in North Wales, and this corresponds to the site class action for moderate class. As I said, this work is underway. The national annex is not completed, and here I use simply the values provided the ROCO date, but some of them must be calibrated for the UK. So I conclude saying that this is probably it's an exciting time to start to plan for the next generation national hazard maps, because there is a growing interest in developing methodology or tailoring methodology for low to moderate seismicity areas such as the UK, where the uncertainties in the hazard can be very large and therefore can affect the design of critical infrastructures. The next generation national hazard maps for the UK will take advantage of the development that have been done in the last years. I show you two of them. And in general, will take advantage of a homogenization process of the data collected by BGS in the last decades. An example was the uniformity estimation of uncertainty in ML. It will also capture, hopefully better, the epistemic uncertainty in the input data to develop a source model and ground motion model. Either in we hope that they become a project in the very near future. So one is the development of the first a national scale map for potentially active faults in England and Wales using highest resolution elevation data together with the BGS geological map. This would fill a gap because at the moment for most of the probably all faults in the UK, we really don't know if they're active or they are capable of generating future earthquakes. The second proposal is to make public available all the recordings and process the recordings for the UK and surrounding regions through a public available database. The third one is to a proposal to conduct national seismic risk assessment across the UK. This would be the first one using the hazard maps published in the last 5 years and available the latest methodology for risk analysis. So here there are all the people who contributed to the offshore hazard project, because I didn't do everything obviously alone. And thank you very much to be here until this time, either in person or online. Thank you very much.
Thank you, Ilaria. Really appreciate the effort you've gone to put that material together. Thank you very much. So it's okay. I think we've got time for some Q&A, which would be great. So is it worth splitting the questions to part 1 and part 2? Is yours part 1 question?
Both.
That's excellent.
Yeah.
Okay, we'll go with that.
Yes.
All right. Thank you very much, Ilaria. That was perfect. So I have 2 questions. The first one is about seismicity. The second one is about GMM. For seismicity, it's a general question for the next generation seismic hazard models. Is there any scope to develop time-dependent seismic hazard models, specifically because I'm asking this because we have DAS datasets, DAS cables in eastern and western coasts, and also we have induced seismicity. We can develop, probabilistic models. We can use ETAS model, so we can develop maybe time-dependent seismic hazard models. Is there any plan for doing this?
I don't want to say yes or no, definitely. So I would tend to say no, but so at the moment there is no really methodology accepted to include dependent events in PSHA, basically. So if that moment arrives, we would test it and include in the next generation maps.
Yeah. My second question is very similar. I was thinking if there is any scope to use GMMs developed for example, for western part. We have calibrated GMM for Preston New Road, which I think includes Blackpool, Liverpool, maybe North Wales. Can we use those GMM models for?
So personally, I would keep it probably separate. So the hazard maps would be for tectonic seismicity. Because probably including also induced seismicity, which have a very low seismicity, would introduce a new set of issues that should be problem, and it's also extremely local. So I would tend to say to keep them separate, probably, but again, if in the next few years maybe things will change and there will be strong approach, strong methodology, state of the art to generate unified maps. So,
all right, thank you very much. Thanks.
Thank you.
Very good. We go to Guillermo and then Ziggy.
Hi, Ilaria, thank you for your presentation. Guillermo Aldana from Jacobs. Just a lot of interesting points you made, but I'm going to keep it just to one question. At the moment, we have two sets of maps, onshore and offshore. And at some points, the difference between one side of the onshore line and the other side are quite important. You mentioned that there is not right or wrong map, which I partially agree. I mean, it doesn't necessarily mean that one of them is wrong. But in industry, it's nice to have some sort of coherence between the two sets of calculations. Is there any plan update on the offshore maps, or even better, an update that incorporates both models into one single set of maps for onshore and offshore, so you eliminate these boundaries, these issues with some of the boundaries?
So the short answer is no. So there's no plan to update the onshore hazard maps now. So I understand the point, the open question. So we don't publish the onshore, the values onshore derived from the 2024 hazard models, because the national hazard map was published 5 years ago and is currently used to update the national hazard maps. I acknowledge that there is this new set of maps done after a short time, and they show certain difference, particularly in the eastern coast. So I don't have a specific answer to your point, and we are not going to update the onshore map now for the moment. At the moment.
Can I have the second question?
I think Ziggy, just before you do, I think Ziggy wanted to come in there.
Yeah, I'm going to speak on behalf of the BSI 525/8 committee, where we've recognised the difference. The decision that will be made is that the onshore maps are for onshore and anything in the water that links to shore, just sort of the 1 kilometre or so around the coastline. And the offshore maps are for stuff offshore. And now, pipeline that comes onshore or something like that, you'll have to make a decision. But that's the decision that's been made. Unless Jacobs want to pay for another study.
I don't think that will ever be the case.
No, I don't think so either.
But then my follow-up question would be, if we were to do a site-specific hazard assessment for the UK, which set of because the main difference here is not on the ground motion characterization, it's on the seismic source characterization. Which seismic source characterization would you use, 2024 or 2020? Or offshore site? Because it will make a difference.
So probably I would use the 2020 onshore, considering also sensitivity analysis of how much the hazard change using, for example, completeness threshold for defined in 2024.
Thank you.
Is it right? Ziggy, do you have any further questions?
Yeah, I just wanted to say I commend everybody to look at the offshore maps, especially when we know that the ISO 19901 Part 2, which is recently updated, has a load of rubbish in the appendix in terms of the offshore maps, not just for the North Sea, but for the whole world. Somebody's made a digital aberration in those maps, and they're not worth the paper they're written on or the pixels that they use. So please use the offshore maps that Ilaria has spent a lot of time putting together for the North Sea rather than the ISO maps.
Thank you.
Thank you, Ziggy. Is it right if we divert online? Because we've actually got a couple of interesting questions here, and then we've got three questions. The first was about the use of AI in future developments of the hazard map, whether you could provide any comment on that, Ilaria. And the second one pertained to starting to incorporate geodetics, whether it's seafloor or wider geodetic data. So could you provide comments on those two topics?
Yeah, so about the first question for the AI, so there are already, it's already used to increase, to enhance the earthquake catalog. So there are several studies also in the UK, not probably in the UK, the AI has been tested on the PNR, so the earthquake catalog in Blackpool for the new seismicity, and has been, you can see that you can increase significantly the number of events in the catalog using the machine learning approach. So definitely there is space to improve, particularly the earthquake catalog. I think there are also a few studies to use it for the ground motion, but it's still, I think they are not ready to be applied for a PSHA, basically. So this first part. The second part was
But geodetic data.
geodetic data.
Yeah.
So for the UK, the geodetic data unfortunately cannot really be used or will not provide a final answer because the series are too short. Started to be computed too recently to be able to provide a significant difference in the development of the source model.
Okay, thank you. And then just the third question was about the plans to develop hazard maps for longer return periods, say 10,000 years.
Basically, this depends on the requirements. So we use a return period indicated by the Geocodate, and usually at a national and regional level, the return period is smaller than 10,000 year return period. To use such a long return period, you need also to consider some other factors. For example, the recurrence interval of very large earthquakes, and in that case, you would also need to do a capable fault assessment, which was not really part of the national hazard maps. So the quick answer is if the guidelines change in the near future, we would consider a longer return period. At the moment, the Eurocode 8 and also the new version of the Eurocode 8 exclude such a longer return period. So because you would need to consider new issues of problem to solve, which is outside the scope.
Understood. Thank you. That's okay. Any further comments from the room then? Let's go to Ian at the front.
Thanks for a fascinating talk. That's amazing. I'm a sort of a lightweight in this subject area of earthquakes and the hazard. I thought some of the maps, bearing in mind we're talking offshore, some of the hazard maps that you were presenting, right up in the top right-hand corner, as you perhaps get nearer Norway, there's a lot of activity up there. Do you correlate with what Norway are doing, or are they not up to this?
In general, the northern North Sea, so the part of the North Sea that is closer to the Norway has definitely more seismic activity than the central North Sea, which is closer to the UK. So it's strongly related to the seismic activity. There is no indication. I mean, there might be also can be also induced seismicity due to operation there, but there are no final evidence for an answer in that direction. So it's considered all tectonic seismicity so far.
Thank you. I was interested in the correlation as well with what's going on in Norway. Do your sort of seismicity history match with theirs on their side of the North Sea? Because there must be some divide. I don't think you don't go right across the North Sea.
Yeah, no, exactly. I consider it the coastal line of Norway, but I didn't really analyze the seismicity onshore in Norway.
Fair enough.
So.
Obvious reasons there. Thank you very much.
Okay, let's just dive. We've got a couple of interesting questions come up again online. This one, close to my heart, this one. I'll read the comment. Thank you for the great talk. It'd be very useful for the community to have a ground ocean database. I think we'd all agree on that. However, site characterization is not so good in the UK. The GVS30 measurements lack at most of those monitoring stations. I wonder whether there are some plans to collect VS30 data to better constrain the site components. Now, I can say this topic has been discussed at length and things are developing. Ilaria, do you want to, or perhaps even David, want to comment any further?
Definitely, I mean, that's another drawback probably of the ground motion component side. I think there are some potential proposal, potential near future project to improve the site characterization of the monitoring stations in the UK. We hope to have improved this component for the next generation hazard maps. There is nothing really certain at the moment. Probably depends on the funding side. Who is going to pay for that?
I think I can add to that as there's a group in the UK called the BGS Customer Group, which is a collection of industry and other members who contribute financially to the running of the network. And this topic is one which is being actively considered because from a UK perspective, we have got to take this forward. I think if we're going to improve the usable data set which we have. So yeah, great question. And I've got one more here, more of a general topic on your thoughts, Ilaria, on how induced seismicity could be included in seismic hazard assessments.
I usually work on tectonic seismicity, so other people in the team work on this seismicity. So probably I'm not the most expert to answer to this question. Generally speaking, the approach for the computation of the rate of occurrence of future earthquakes in the context of induced seismicity change compared to the tectonic seismicity. So the formalism then change, and so far I've been concentrating on tectonic seismicity. So.
Okay, fabulous. Any final questions from the room?
I've got a question if I
David.
can use my position as microphone holder. A lot of the uncertainties are understandable because you've had to do really clever things due to the lack of sensor data from the North Sea or from our coastal region generally, because it's so phenomenally expensive to get sensors into the sea. But there's always there's DAS systems coming online. There's talk of consortiums paying for OBS sensors. In this brave new world, we have better sensor coverage of places like the North Sea. How quickly will that actually start to make a difference to your calculations of seismic hazard offshore?
Probably would not make any difference because then you would need a longer catalog. I mean, basically the best that would make big difference if you have an earthquake, a strong earthquake, a large earthquake. That would be ideal, but we don't. I guess for that.
Thank you.
So you would need decades.
Yeah.
To see a difference.
Yeah, thank you, David. Okay, so in the absence of further questions, we'll close there. Please note the citation reference. Did you get that? Ilaria nicely amplified that, so we want to make sure we get that right. So, and the feedback QR code. Very good. Very good. That's going to come up next, I've been told. Yeah. So final thanks. Thank you for the effort and the preparation, Ilaria. It's greatly appreciated. There it is.